if I draw a picture of the Earth, there's a gravitational field that surrounds the Earth. And that gravitational field is a region or an area where a gravitational force could be experienced. We draw the gravitational field as pointing towards the Earth or pointing towards any big mass. And just because I define the gravitational field as a region in which a gravitational force could be experienced doesn't mean there's actually a gravitational force being experienced there, right? What do we need in order to have a gravitational force actually experienced? What do we need in addition to what you see up on the board right now? Yeah. To feel it, to experience it, right. So this is the Earth. This is what's causing the field. In order to have a force, you actually need something to experience the field as well. Maybe you put a ball in that gravitational field. We make the field, or we define the field, as the region in which a force could be felt if there was something there. Even if I take that object away, though, there could be a force felt there if there was something there. The gravitational field is just a nice way of explaining gravity without the need to have something feeling or experiencing gravity. Well, we have a similar concept with electricity. We have an electric field that is a region in which an electric force could be experienced by something if there was something there to experience it, right? If I was to draw this as my electric field, what kind of charged particle would this be causing this electric field? A positive or a negative, Daniel? This would be a negative, because we define the direction of that electric field as the way that a positive particle would move if placed in the field. Let's put a positive particle right here. What would happen to that? Let's pretend I don't have that field line drawn for a second. Okay, I put a positive particle right there. What would happen to it if I put it in that spot in the field? It would get drawn in, right? It would get drawn towards it. So we define the direction of that field as toward the negative, because that's the way that a positive would move when placed in that field. Now, if I happen to put a negative in that field, what would happen to it? It would get pushed away. It would go this way, right? That doesn't mean the field points to the left. The field is the way that a positive would move if placed in the field. And if I put a positive right here, it would still move to the right. Hey, it would move toward the negative charge in the direction of the field. Okay, it doesn't have to be there to be able to say the field is the direction that the force would be if it was there. Okay? Positive goes in the direction of the field. Negative goes opposite to the direction of the field. What's the quote that we had on Thursday that helps us remember that? I'm positive the force is with the field. Okay, that reminds us, hopefully at least it reminds us, that this positive particle will always experience the force in the direction of the field, and the negative particle will always experience a force opposite to the direction of the field. Here's our electric field. This is where we finished off on Thursday. Here's our electric field, and let's say we've got in this electric field a positive particle right here and a negative particle right here. Let's say that green is going to represent the velocity of the particle, which way the particle is moving. Let's say in both cases the particle is moving downward toward the bottom of the page. Which way is the electric force going to act on this positive particle? Downward, right? Okay, I'm positive the force acts with the field. I'm positive the force is in the direction of the field. So if we're drawing the electric field as pointing downwards and we have a positive particle, then the force must be downwards as well. What's going to happen to that positive particle as a result of it moving downwards and the force also acting downwards? It's going to speed up. It's going to accelerate, right? Now we got a negative particle. It's moving downwards as well, just as the positive particle is moving. Which way is the force acting on it? Upwards, opposite to the direction of the field. Doesn't matter what caused the field, a negative particle always experiences an electric force opposite to the field. Now what's going to happen to that particle? It's moving downward, it's going to slow down, right? It's going to decelerate as a result of downward movement and upward force. Now, what if we have our positive particle, both our positive particle and our negative particle moving to the right? Which way is the electric force on the positive particle now? There's no trick to this. It's downward. I'm positive the force is with the field. If the field is downward, then the force is downward. Regardless of which way the particle is moving, It's irrelevant completely. If the field is downward, the force is downward. Right, Chase? What about this one? Field is downward on this negative particle that's moving to the right. Which way is the force, Josh? Upward. Opposite to the field. Just like it was in the last one, the field is opposite to the force if we've got a negative particle. Now, in the first one that I drew, we saw that the particle would accelerate. It would speed up in the direction of motion of the particle. In the second one, it would slow down in the direction of motion of the particle. What's going to happen to the third one here? What's the path of this one going to look like? Yeah, it's going to kind of curve downwards like this, which reminds us of what from Physics 20? Projectile motion, right? When you kick a soccer ball off the roof of a building, horizontally off the roof of a building, it experiences only one force, and that's gravity, pulling it down. And that causes it to go in a parabolic path as a projectile. Okay, we solved those problems last year quite a bit, right? Those projectile motion problems. This is exactly the same thing. This follows a parabolic path as well, because it's like the soccer ball being kicked off the edge of a building horizontally, experiencing a downward force. What about this one? What about the negative particle? What's the shape of that path going to be? It's also going to be a parabola, except it's a parabola that's flipped over, right? Because in this case, instead of going horizontally off of the edge of the building and experiencing a downward force of gravity, it's like going horizontally off of the edge of a building and having like an anti-gravity or something pushing it up. Same shape, but it just curves in the opposite direction. Okay, that make sense? All right, what I want to do today is focus on the mathematics of electric fields. In Physics 20, you learn 3 equations that describe gravity. The first one, F is equal to G m1 m2 over r squared, isn't really an electric field equation. This is an electric force equation. But it does have an analogous equation with electricity. We've done it already. What is the analogous equation with electricity? The equation that is like Newton's law of universal gravitation for gravity. Yeah, it's Coulomb's law. We say F is equal to kq1 q2 over r squared. So we've used that quite a bit already, right? We know what that means, right? We know what all the variables in there are. K is the constant, charge 1, charge 2, and the distance that separates them. It looks remarkably like Newton's law of universal gravitation, except that we're not dealing with masses, we're dealing with charges. This second equation is for electric field, for gravitational field. This second equation describes the field caused by a producer, something that causes a field. If I have my board marker a certain distance above the surface of the Earth, the board marker experiences a field that's caused by the Earth. If we knew data about the Earth, what caused the field, then we would use this equation. The analogous equation in electricity is E. Be careful with this. Make sure when you're talking about electric field that you put that little vector sign over top of it. We know that electric field is a vector field, so it's important for that reason. But even bigger than that, if we forget to put that vector sign over it, at some point, all of you, every single one of you, at some point, if you don't put that vector sign over it, will get it mixed up with what? Energy. And right now, when you see this equation, you're going to be like, oh, there's no way I'm ever going to get that mixed up with energy. Trust me, you will. And you might still get it mixed up with energy at some point, even if you do put the vector sign over it. But you're a lot less likely to get it mixed up if you remember the vector sign, because it's a way of distinguishing between electric field and what you're used to seeing as the symbol for energy. So electric field, 2 absolute value signs around it, just telling us that the equation that I'm about to write down here isn't going to tell you the direction of the field, even though it is a vector field. It's only going to give you the magnitude. We'll have to figure out the direction some other way. Anybody want to take a stab at what that equation is going to look like? Very good? Good. KQ over R squared. K is, of course, the constant. R is the distance from the producer. Which is going to be measured in meters, of course. And Q would be the charge. Charge of what? If we were looking at this equation for gravity, using the example of the Earth and my board marker that's in my hand, what mass would I use in that equation? The mass of the Earth that's causing the gravitational field, or the mass of the board marker that's experiencing it? We'd use the mass of the Earth. We'd use the mass of whatever is causing the field. In this case, we're going to use the charge of whatever is causing the field, the charge of the producer. And that's going to be measured in coulombs, of course. Be careful with that because you often see the charge in microcoulombs or even sometimes nanocoulombs. This last equation down here, G is equal to Fg over m. This would be the field that was experienced by the board marker in the Earth's gravitational field. We'll call this my experiencer equation. We use it whenever we have information about what feels the field. You experience the Earth's gravitational field. If we knew something about you in the context of gravity, then we could use this equation to describe it. If we knew something about the Earth, then we'd use the producer equation. What's the analogous equation of this one? E is equal to the electric force, Fe over Q. Yeah, the electric force over the charge. That's going to be measured in newtons, and this Q would be the charge of what? Yes, it's the charge of the experiencer. Good. And that's going to be, of course, in coulombs. Now, on your data sheet, it doesn't have this. If it was up to me, it would. On your data sheet, you don't see these absolute value signs around these two variables in this equation. So what they're telling you is, by not putting those absolute value signs in there, is that this equation can provide for you the magnitude and the direction of the electric field. I'm telling you, you shouldn't try to do that. You shouldn't try to find the direction of the field using this equation. You should find the direction of the field some other way. So, because of that, I'm going to stick in those absolute value signs. If you forget to put those in, it's not the end of the world. You're probably not going to get the question wrong because you forget the absolute value signs. It's critical that you put the vector sign. The absolute value signs, it's not really that big of a deal. Okay, but I'm putting them there because I want to be correct in the way that I'm using this equation, and that is that I'm not going to find the direction with the equation. I'm going to find it some other way. Okay, finally, what do you think the units are for electric field? We've identified the units for all the variables within it, within the equation. What do you think the units are for electric field? Somebody said it? Daniel? I think you said it. Newtons over coulombs. Good. We can get that from the experiencer equation. We see force over charge. That would be newtons over coulombs, right? Even in this one, if you look more closely at it, this is newtons over coulombs as well. K is Newton times meter squared per coulomb squared. Q is coulombs. And R squared is meters squared. That looks kind of ugly, but if you start canceling things off, what are we left with? Just the same as the experiencer equation, we're left with newtons per coulomb. Just like with gravity, gravitational field was newtons per kilogram. Right? Newtons per coulomb, newtons per kilogram. Make sense? Okay, I want to take a look at an example that's on the handout that I gave you at the beginning of the unit. Number 1 says, determine the electric field strength and direction 50 centimeters to the right of a sphere that has a negative charge of 25 microcoulombs. Few things to circle here. microcoulombs, centimeters, negative charge. Some of you may look at this question right now and be able to determine quite easily whether this is a producer or an experiencer. Some of you may not be able to determine right away whether it's a producer or an experiencer. Here's what I would suggest you do if you're having any trouble distinguishing between producer and experiencer. Draw a picture. I have a sphere that has a charge here of negative 25 microcoulombs. I want to find the field strength 50 centimeters to the right of that. So I want to find the field strength where that x is, right? This must be a producer. It cannot experience a field at a point where it isn't present. It's like, let's say it's not so cold outside today, but let's pretend it is. Let's pretend it's minus 20 outside today. You can't experience that temperature, that coldness, if you're not at the place where it's cold. In order to experience something, you need to be there to experience it. This 25 microcoulombs is 50 centimeters away from that spot. I want to find the field at that spot. This 25 microcoulombs can't possibly experience the field when it's not there. Therefore, it must be a what? If it can't experience it, it must be a producer. Right. We're going to use the producer equation. We've already got our givens basically written down here. So let's just go straight to our producer equation and see if we can solve this now. KQ over R squared. Let's say K is 8.99 times 10 to the 9. Q is 25 times 10 to the minus 6 coulombs. Not negative because I always drop the sign of a charge when I sub it into an equation. 10 to the minus 6 because it's microcoulombs. And I remember to put the 10 to the minus 6 because I circled it up above. Divided by R squared, 0.50 meters squared. When I sub that into my calculator, I get 8.99 times 10 to the 5. What are the units again? Newtons per coulomb. Now, we're looking for the direction here as well. The equation didn't tell me what the direction was, right? Gave me the absolute value. How do I figure out the direction? Well, this diagram that I used to determine that I had a producer is helpful now as well. I'm trying to find the field strength to the right of a negative particle. Which way does the field point surrounding a negative particle? Towards it. So this field would point this way toward a negative. The field is going to point to the left. Now, if I was looking for the field strength over here to the left of a negative particle, which way would the field point? To the right, right? It would point toward the negative producer. I don't need an equation to tell me the direction. My picture can tell me the direction, but I do need the equation to give me the magnitude. All right, I'm going to ask you now to take a peek at worksheet number 8, and specifically on worksheet number 8, I'd like you to do, for now at least, the first 4 questions on worksheet number 8. All right, let's have a look at question number 5 here. It says, calculate the magnitude of the electric field experienced by the electron if the net force experienced is 6.5 times 10 to the negative 16 newtons. Clearly, I think when you read this question, this is an experiencer. Like when you see the word experienced twice in the same sentence, experienced by an electron, experienced, okay, this is an experiencer. This is feeling the field. So we're going to use the experiencer equation, E is equal to F over Q. The force here, the force we're given is 6.5 times 10 to the negative 16 newtons. That's what that force is supposed to stand for, right? F is supposed to stand for the force experienced or felt. Q is the charge of the experiencer, and the experiencer is the electron. So it's 1.60 times 10 to the minus 19 coulombs. We know that an electron is a negative charge, but you also know that we always drop the sign of the charge when we're subbing it into an equation. When we do the math there, we end up getting, for this one, 4.06 times 10 to the 3 newtons per coulomb. Now, a couple people are asking me about the direction of this. Do we have to include the direction? No, you don't have to include the direction because you were only asked for the magnitude. But even if it didn't say just the magnitude, there's no way of getting a direction for this, right? There's no frame of reference. Okay? If we're told the net force is to the left, then we would know the field would be to the... Anyone? To the right, because it's a negative particle, experiences a force opposite to the field. If the force was downward, the field would be upwards, right? But we don't have that frame of reference, so even if we wanted to in this question, we couldn't determine the direction of the electric field, but we're only asked for the magnitude anyways, so we don't have to go there anyways. All right, let's take a look at one more example. And then you guys will work on a couple questions and we'll wrap it up for the day. This one is the third one on your sheet. It says determine the magnitude and direction of the electric field midway between this charge and this charge that are 20 centimeters apart. If there was ever an electric field question where it was critical to draw the diagram, this is it. There's other questions where I think it's useful to draw them. Questions 1, 2, 3, 4, I think it was very useful to draw the diagram. It's critical that you draw the diagram here. So we say we have a 100 microcoulomb charge, and then we have another one that is negative 75 microcoulombs. And they're 20 centimeters apart. We want to find the field strength right there. Now, what I want you to do, first of all, let's identify, before we worry about direction here, let's identify, if we're trying to find the field strength at point X, are these charges, the 100 and the negative 75, are they producers or experiencers? They're producers. We're trying to find the field strength somewhere else, not where the charges are, but somewhere where the charges aren't. This 100 can't experience a field right there if it's not there. It has to be a producer, as does the 75 have to be a producer. Now, let's determine the direction of the fields now caused by the 100 and the 75. Let's pretend for a second that the 75 microcoulomb charge isn't there. The field right here to the right of 100 points which way? To the right. It points away from the positive. Agreed? Points away from the positive. Now, what about this one? We have a 75 that has a negative sign associated with it. To the left of a negative, the field points which way? To the right, because it points toward the negative. So one of the fields is to the right because it's away from a positive. One of the fields is to the right because it's toward a negative. Does that make sense? Let's calculate both of those fields, the magnitudes of both of them, that is. E1 is equal to KQ1 over R squared. Q1 is 100 times 10 to the minus 6, because it's microcoulombs, divided by, what's the distance I use here? 10. Who said 10? Good. We're actually going to make it 0.10, right? because it's got to be meters. Why is it 10 or 0.1 as opposed to 20? Yeah, we want to find the field strength midway between, which is 10 centimeters away from the 100 coulomb charge, 100 microcoulomb charge. Okay, we do the math there. That one works out to be, I believe, 8.99 times 10 to the 7. Is that right? Somebody just double check that because I had made a mistake earlier. And 8.99 times 10 to the 7. That would be newtons per coulomb. And similarly, we would find the field caused by number 2 to have a value of 6.7425 times 10 to the 7 newtons per coulomb. And then we go to add them up. Positive or negatives. Now we put positives in them, right? We drop the sign of a charge, but now we're talking about direction now, right? So we go to add these up, we're going to make them both positive because they're both to the right. That gives me 1.57, I think, times 10 to the 8 newtons per coulomb. Is that right? I got a positive value for it, which means it's to the right. Of course it's to the right. If both fields are pointing to the right, the net electric field is going to point to the right as well. You're going to find that when you go to do questions 8 and 9 on your worksheet, which is what I'm going to tell you to do next, question 8 is real similar to what you just did. Question 9 has 3 charges. So here's charge 1, here's charge 2, here's charge 3, and you want to find the field strength over there. How does that change things? Not really much at all, right? Except that you would have 3 electric fields that you have to add up instead of 2. Same idea though, right? Draw your diagram, determine which direction all 3 fields are, and then add them all up with the right signs, and you're good to go. Yeah, question?
So for the last example,
Yep.
how are we supposed to tell which side to put the charges on? Because initially I wrote the 100 or the 70 negative 70.
Oh, that's a good question, actually. That's a really good question, actually. This question isn't clear on that, actually. I did it this way because I made up the question. I just did what I knew that I meant to do. But it's not stated real well at all. So the question, if you didn't hear that, guys, was how do we know which side to put the 100 on and the negative 75 on? It should absolutely say. It should absolutely say the 75 is to the right of the 100. Okay? I just didn't need it to say that because I knew what it was supposed to say because I had made it up. The only thing that you couldn't really tell, Regan, by this question with the way that I've stated it, is that the electric field's magnitude is 1.57 because they do have to be in the same direction. Now, whether they're both to the right or both to the left, that determines on how you drew your picture. And since it's not clear, I'd have to give you value in both cases there. Okay? Good question. All right, so let's take a look then at your worksheet, specifically questions 8 and 9 on your worksheet, please.